What do you mean mathematically by turning a sphere inside out?
Well, there are various ways to look at a question. The easiest way to turn, say, a ball inside out is to rip a hole in it and turn it inside out through the hole. But that is not nice because once you've put a hole in it, it's no longer a sphere. So another way is to let the surface pass through itself, as it does on this model. That leads to a more interesting solution. The bottom part of the sphere has been pushed through the top part and made this hump here where the inside surface is showing. You can see this surface comes from below, passes right through this top surface and comes out here. So there is no hole or discontinuity. The surfaces just cross each other here. In fact, we can see this in computer animation. The sphere is partway inside out now because when you push the bottom surface up, you're seeing the back of that surface here. And if I continue to pull this through, the sphere could turn all the way inside out.
Yes, but if you did that, you'd end up with a cusp or a corner around the perimeter.
That's right. The trouble with the cusp is that the surface is not smooth there. And one of the things that you'd naturally want to require for turning a sphere inside out is that you don't make any creases in the surface. So the real question is, can you turn a sphere inside out, allowing the surface to pass through itself, but not producing any creases?
When was this kind of mathematics worked out?
This is a fairly recent idea in mathematics. Steve Smale was the first person to consider and answer the question.
Yes, it was 15 years ago that I was working on a general problem which had as one of its implications that a sphere could be turned inside out. So naturally enough, I tried myself to turn a sphere inside out. I made many attempts, and I failed in those attempts. But one thing I learned from these attempts was that it seemed indeed possible that one might be able to turn a sphere inside out. And that possibility gave me confidence to go ahead and to complete the analytic proofs required by the general theory. Even after I had done that, I still didn't see how to explicitly turn the sphere inside out. And it was only sometime later, when Arnold Shapiro had heard about my results, that he constructed an explicit method for turning the sphere inside out. Since then, several people have worked on this process, and I think the finest representation of this is in Charles Pugh's models.
Charles, what led you to actually decide to build models? Because it must have taken quite a while, quite a lot of work.
Well, it did. But the reason I was doing it was because I was trying to understand the geometry that's implied by Steve's theorem. That Steve's theorem is completely abstract and doesn't mention too much geometry in it. At least you can't see the geometry. These models are an attempt to see what's going on. And many people tried to see what was going on, including Arnold Shapiro, also including Bernard Morin, who is a blind French mathematician. He's the one that invented the homotopy which these models represent.
I take exception to your saying that my theory is completely abstract.
Well,
actually, implicit in the theory
in principle, you can make geometric models from your theory. However, no one was able to. Everyone else constructed these homotopies, realizing that your theorem was true and that there had to be such a homotopy, and then they went ahead and made their own, not from your theorem. Nevertheless, it's true. There is geometry in here. The way I made these models is sort of interesting. I took chicken wire and I cut it into pieces, and then I bent it over this kind of a pipe, as you see, to make it curved like that. Then I would cut other pieces and solder them together to make a continuous surface, or at least an apparently continuous surface. And the way I was able to make the one surface appear to pass through itself, or through another part of itself, is by, when I cut the chicken wire, I would only cut 2 pieces and then solder them across an uncut piece like this, so that I would be reconnecting ends of the chicken wire which I had just finished cutting. Now, let me give you a tour of the models. one starts with the sphere in its round shape and begins to push the back towards the front. And that first step is shown in this model, where the back has been pushed towards the front. This is still the front. The back is now touching the front at one point right in the middle. This shows how the back has now been pushed out. And here's where the back, this used to be the back. It's now intersecting the front along this curve, which is a deformed circle.
And the surface we actually see here is in fact what was the inside of the back.
That's right. So it's beginning to protrude, starting to turn inside out. Now, the next step shows how the two sides of this part of the surface are pushing toward each other. As my two hands push together, these surfaces are pushing together. You can see that from here. This surface is going towards that one, although it's still the same topologically as it was a minute ago. I like to think of this as a hat. This is the crown of the hat. This is the brim. And the next stage shows how the two sides of the crown have been pushed toward each other and have even touched. Similar to what happened in the first step. As you can see, the hat is beginning to be twisted. That is to say, the top is twisting one direction, the bottom the opposite. Now here you can see how this is, again, an example of further twisting. The top is twisted a little more, the bottom a little more, and this is the result. Now I like to think of this as an ear, and that as another ear. This is an eardrum, that as another eardrum. The process twists one ear in one direction, the other in the other direction. This model shows further twisting.
So the surfaces are actually continuing to move past each other as you twist.
That's right. The more you twist, the more they move past each other.
Oh.
That's the principle. The main step, the main mathematical step, really occurs between this model and the next. And perhaps it's best seen here, where the thing to concentrate on is this surface here and its relation to this surface here. The process which occurs I like to imagine as water rising across an isthmus. I think of this as an isthmus, and this is one ocean, this is the other. The oceans are rising, or else the isthmus is sinking, and they will overflow this low part of the isthmus. Now, that can be seen in this model here. The corresponding place is here. This used to be the ocean. It's still the ocean, and it's risen above what used to be the isthmus, which is here. Now the next step in the process, again caused by further twisting, is that this tube will rise. It will appear to come out towards the front. This tube here will appear to recede towards the back, and they will begin to cross each other. You can see that's partially occurred here, where the tube which used to be entirely behind this tube has risen out. And as it did so, it created two triple points. A triple point is where three surfaces intersect in a point. Now this tube rises out a little further and becomes at an equal level with this overlying tube. This used to be the crown of the hat. This used to be the front of the sphere. Now if one can come to this perfectly symmetrical position, then by merely a 90-degree rotation in that axis of symmetry, and then reversing the models just as we've seen them come up,
Yes.
the process will end out with a perfectly round sphere, except what used to be the inside would become the outside.
Well, actually, what you have here is fourfold symmetry, isn't it? Because
That's true.
back in these earlier models, there was a twofold rotation axis. And now you've gained higher symmetry still than that.
That's true. At every stage until now, there's been twofold symmetry.
Yes.
At this stage, fourfold symmetry.
At this, yes. Actually, the quadruple point is probably more fundamental than the fact of fourfold symmetry. Because you could distort parts of this without losing the topological
That's correct.
character.
I put the fourfold symmetry in it because it looked pretty.
And it does help to see what, sort of, for me at least, to comprehend what I'm looking at.
It organizes it.
Yes.
Now, of course, you can't move this kind of surface very far, and so that's why Nelson has done the rest with computer animation.
What I did was measure various points on these surfaces and describe it to the computer, actually using a bunch of small patches of the surface that might correspond to a piece of this shape. And I'd find where on the model the coordinates of these vertices were, and also describe the tangent planes at each of these vertices, so the computer could figure that it must have been curved around in this way. And then I arranged it so the next piece would fit on in a continuous way. Then after I had each of the models in the computer, I told the computer to move the corresponding vertices, in a smooth way from one model to the next, so it could show the intermediate frames of the movie.